Thank you for your introduction. My name is Itoh from Wisconsin University. Sorry. My research topic is grip behavior of titanium and aluminum alloy using miniature testing approach. First of all, I will introduce the background of this study. In modern times, reduction of CO2 to control the greenhouse effect is extremely important. One of the approach to achieve this goal is to conduct the lightweight design for components and the structures. For example, here it shows the turbocharger. During working condition, turbocharger is subject to thermal loading or some mechanical loading in high temperature. Therefore, the grip strength for material for manufacture the turbocharge is necessary. Therefore, in general speaking, nickel-based superalloy is used to manufacture the turbocharge or jet engine blade. However, the density of nickel-based superalloy is too high to achieve the objective of lightweight design. Recently, titanium alloy and aluminum alloy has been paid attention because it has high specific strength and excellent mechanical properties at high temperature. As previously mentioned, the turbocharge or the jet engine blade during working conditions, they subject to grip loading or grip damage. Therefore, one of the main fracture mode is grip fracture. Therefore, before applying this material to engineering application, investigation the grip properties is very important. Usually, we obtain a new material grip properties by using the grip testing and using the standard specimen. However, there are some issue in this method. For example, the large specimen or large size material is required for standard grip test. So if we have a new material that made by SPS method. So as I know the maximum size for material made by SPS method is less than 20 millimeter. So if we want to know the grip properties of this material, testing using the standard specimen method is unavailable. And another question is that evaluating remaining grip rupture time is also unavailable using the standard specimen method. Therefore, development or validation of the miniature grip testing technology is very important. Therefore, the objective of our research is investigating grip properties of this material using miniature specimen method and serving the side effect on grip tester grip rupture time. And here gives the experiment method. This figure shows the grip testing machine we used. It is developed by ourselves, and the specification is given here. The maximum loading is 1 kilonewton, and the test temperature range is from room temperature to 800 degrees. And the loading mode is lever types. The ratio is 1:5. We use the LVDT to measure the strength during grip test, and the test condition is given here. Due to the titanium and aluminum alloy has good high temperature properties, so we choose the 760 degree to conduct the grip test. The stress level is given here. We use 4 stress level to test the grip strength and the environmental. So in order to investigate the oxidation effect on grip life, we use 3 air flow to conduct the grip test, which are 0, 75, and 150. The unit is given here. The material is a tightly forged titanium and aluminum alloy, which has a triple microstructure. The microstructure is given here. Here we can see that the large green is the laminar phase, and the white green is the gamma phase, and the dark green is beta phase. The miniature specimen used in this study is given here. The total length of the specimen is 35 millimeter. Its gauge length is 10 millimeter with diameter of 2 millimeters. The grip test result given here for the blue point. This is the grip result tested using standard specimen obtained by Professor Hiyoshi at the University of Fukui, Japan. From this figure, we can see that at high test level or shorter rupture time, the vertical difference not so large. However, with the decreasing of applied stress, the gap between standard specimen and the miniature specimen increased. Moreover, we can also see that at relative low test stress level, the air gas flow also affects the grip length. For example, for this case, the air gas flow with high flow, the grip life is longer than that with low flow condition. Another one is the grip strain rate. From this figure, we can also obtain some similar conclusion, which is that the minimum strain rate for standard specimen is the lowest among those test series, and test in low air flow is the higher. The test result on the low air flow with much higher the minimal grip strain rate. From this figure, we can see that although the side effect on the grip rupture time, however, we can see that if we use the non-common ground rule to predict the grip life, we can see that we can use the one master curve to predict all the test conditions. And moreover, for the Norton rule, we can see that it is the relation between the applied stress and the minimum grip strain rate. So we know that the dominant factor for grip rupture time is the minimum grip strain rate. So we can see that at the same applied stress level, the minimum grip strain rates are very different because of size effect or oxidation effect. Here we show the oxidation behavior. Only 3 typical testing specimen is given here. The test condition is given here. We can see that at the same applied stress level, all of tests are using the miniature specimen. At the same test stress level with different air flow, 150, 75, and 0. We can see that the thickness of the oxidation layer increased with decreasing the oxidation scale. The thickness of oxidation scale increased with decreasing of air flow. Therefore, we know that even testing in the air gas condition, oxidation scale also formed. Later, I will discussing the reason. So in order to qualitatively analyze the oxidation scale growth rate, we did lots of tests and measure the thickness of the oxidation layer. And here we can see that the oxidation scale growth rate for air condition or air loading condition is the fastest, and test the growth rate for air gas flow of 150 is the lowest one. After that, we correct the grip life using 4 methods. One we call the damage correction. Here we can see the method given here. The first of all, we calculate the scale growth rate by using this graph for corresponding for the relative test condition. And then we correct the really stress by using this curve. The illustration is given here. After that, we calculate the relative grip rupture time. Finally, we use the linear damage rule to calculate the damage. When the damage becomes 1, we think that the grip fracture occurred, and the corresponding life is the correct grip life. And also this method is usually used in miniature test series. It's called the stress Jordan. Here is we assume that the oxidation scale formed at the time of fracture is present from the early stage of the test. So we only correct the really stress without condition under other parameter. And the third one we call the theta project correction. So we know that we can use the theta project method to join or representing a grip curve here by correcting the stress and substitute it into the theta project method. We can calculate the grip strength. When the grip strength becomes the rupture strength, we think grip rupture occurred and the corresponding life is the correct life. The method 4 is also similar to method 3. The only difference is that this method considers that the real stress was affected not only by the oxidation but also by the grip strength. So we use this equation to correct the real stress and then substitute it into theta project method, and other processes are the same to the upper rank. And here is the correct result. From this figure, we can see that almost all correct results are distributed in plus minus 2 factor line. However, when we quantitatively analyze the error for the 4 method using the following 3 standard, we call the IMSE, MAE, and MAPE, we can see that the damage correction and the theta project are not so good. And for stress correction method and theta project method, the IMSE of theta project method is slightly higher than stress correction method. However, the other 2 standard of MAE and MAP are almost the same. However, we consider that this method is too complex. And this method is very simple. We recommended that when we correct the grip life for miniature specimen, we can use the stress correction method. And finally, I want to discuss the oxidation grip loading assistant oxidation mechanism. So why? So from this figure, we can see that the oxidation behavior under grip loading is much higher. The oxidation growth rate is much higher than loading-free condition. So here we give some explanation for loading-free condition. At the early stage, the oxidation layer grows by oxygen ion, a diffusion inward, and the titanium and aluminum ion diffusion outward, and the scale formed. With the increasing of the oxidation time, the oxidation scale grows linearly. And however, if there is a loading, if it is tested under the grip loading at the early stage, the mechanism is almost the same. However, with the increase of the testing time and the strength increasing, so many microcurrents were formed in oxygen scale, so much more oxygen ion can pass through this layer to react with the titanium and aluminum iron. Therefore, the thickness of this the oxidation layer is higher than that one. Okay, the conclusion. Thank you for your attention.